Today let's learn about Kirchhoff's second law, or which we commonly refer to as Kirchhoff's voltage law or the loop rule, or we also call it as KVL in short. Many times we refer to it as KVL. So let's get into the definition of it. Its definition says that the algebraic sum of potential differences in any loop, including those of associated EMFs and those of resistive elements, must be equal to 0. So what does this rule mean? Let's simplify in a simple language. We can say that if we have a closed loop or a closed circuit means, let's take a basic one, that is one resistor connected across a battery, making a closed loop. So what does Kirchhoff's second law say? It says that the algebraic sum of potential difference across this resistor and across this battery or the EMF that we have connected, algebraic sum of the potential difference across these two must be equal to 0, or we can write it in a simple language as that the summation of delta V should be equal to 0. So before we learn how to apply KVL, let's learn the sign conventions first. That how are we going to consider the sign of V in different cases? So if we talk about a circuit, we basically deal with two basic elements that are, first one is the resistor and the second one is the cell or the EMF. Okay, so first let's talk about resistor. If we say that we are traveling across a resistor in a closed loop and the direction in which we are moving is same as the direction of current in the resistor. So always remember that current flows from higher potential to lower potential. So what does the sign convention say? That if we travel in the direction same as the direction of the current, then the value of V is considered as negative, or IR will be negative. You can say it simply. The reverse of it, that when we travel across the resistor in the direction opposite to the direction of current, then we consider V as positive, or IR will be considered as positive. Let's also talk about the cell. So across a cell, we have two terminals in a cell, the longer one and the smaller one. The longer one represents the positive terminal, the smaller one represents the negative terminal. So when inside the cell we are moving from positive to negative, from positive to negative, that is from higher potential to lower potential, then what do we say? That there is a potential drop across the cell, or we consider the value of V to be negative. Whereas if we move from negative to positive, means we are traveling from the negative terminal to the positive terminal, then we say there is a potential gain across the cell, or we can say that the value of V is positive. So these are the four basic things that you need to remember in order to apply KVL to circuits. Let's move ahead. Let's take a simple circuit. Okay, one more thing. Before I talk about applying KVL in this circuit, let me just explain you that why are we in need of KVL? Why cannot we apply Ohm's law directly? Because till now, till the lower in the lower classes, you have studied about Ohm's law, and by applying Ohm's law directly, you can find the current in any circuit. For example, if I consider this circuit and I consider the value of the resistor to be 2 ohm and the battery having a potential of 10 volt, and I ask you that what is the current flowing through this circuit, then you'll simply say that, ma'am, the current will move from higher potential to lower potential. This will be the direction of current across the resistor, and we will simply find out the value of I using the relation V is equal to IR. So I will be equal to V upon R, that is 10 upon 2 or simply 5 ampere. And this is correct. So whenever it is a very simple circuit, it is quite easy to find the value of current. But whenever there will be a series of too many circuits connected together, or there will be a lot of cells connected across a circuit, then it will become difficult to find the value of current in those circuits. And Kirchhoff's law will make it easy. So first let's learn to apply Kirchhoff's voltage law KVL to this simple circuit. So a circuit is given to us, a simple circuit is given to us. Let me name this circuit. I'll begin from terminal A. So I'll move along this direction A, B, C, D, A. Let me name this loop A, B, C, D, A. Now, inside this loop, first step is to take the direction of the loop or the direction of the path in which we are going to move. So it is not at all mandatory that you take any particular direction. You can choose any of the directions, either clockwise or anti-clockwise. For this question, let me take it in the clockwise direction. So if I start moving from terminal A and come back to terminal A, let's see what I do. I move in the direction of current from A to B. Then from B to C, again I am moving in the direction of current. And while moving in the direction of current, I am moving through a resistor. And what do I know? Current flows from higher potential to lower potential. So across the resistor, when I am moving in the direction of the current, the value of V will be considered as negative, or I can simply write minus IR. V is equal to IR, so I'll write it as minus IR. Let's move ahead. Next, moving from C to D, no uh, device is there across C to D. Then from D to A back, there is a cell. Now, when I consider this cell, let me see how am I moving. I am moving from the negative to the positive. So when I'm moving inside the cell from negative to positive, means I'm moving from lower potential to higher potential. And when in the cell we move from lower to higher, value of V is positive. So I can write it as plus V equal to 0. So this will becomes V is equal to IR. Let's take a bit more complicated circuit now. So let's consider the second circuit. Now in this circuit, the direction of the current is given to me, and it's simply my choice that which direction I want to consider for applying KVL. This time let me take anti-clockwise direction. So let me write the loop as A, D, C, B, A. This is the way I'll be moving through the loop. So first moving from A to D, let me see. I'm moving across a resistor and I'm moving in the direction opposite to the direction of resistor. Means the value of IR will be taken as positive. So I can take it as IR2, positive IR2. Next, I come to the battery where there's an EMF of E2 being applied there. So across the cell, I'm moving from higher potential to lower potential. While moving from higher to lower means there is a potential drop, and I'll be considering the potential drop as negative. So minus E2. Let's move ahead from C across the resistor R1. Again, we are moving in the direction opposite to the direction of the current. So when it is opposite to the direction of current, it is taken as positive, means I R1. And then we have a cell E1 connected there, which is in which we are moving from negative to positive, means from lower potential to higher potential, and lower potential to higher potential in a cell considered as positive. So I can write it as plus E1, and this should be equal to 0. So this will be the equation for applying KVL across this circuit. I hope you understood it. Do not get confused with the directions. You can choose any direction, but throughout one loop, that direction should remain the same across all the elements of that particular closed loop. Thank you.